Hi, Aaron. Sorry you're not with us, but there are other things to take care of today. So if I get this up in a timely manner, you'll have last class to watch, which was 3 videos and probably 3 more. So you're going to have a good weekend. All right, let's see how it goes. Most recently, we have been answering the question, does the infinite series converge or diverge? So over here I kind of gathered, and Aaron, if you can't see that, it's small and not really, it's just more for my sake to remember what we've done so we can just discuss it really quick before we go into another test that we can do for convergence and divergence. So the very first thing we did is we took a series such as the summation as n goes from 1 to 0 of 1 plus 2 plus 3. And when we did that, we could look at what was called these partial sums. So can you help me with developing really quickly, what are the partial sums that go with this series? So you want to give me the first term, then you want to give me the first 2 added, then the first 3 added. So Brendan, with that in mind, what are we going to get?
For 1 over n?
For 1 plus 2 plus 3.
Oh. 1, 3, 6.
And 1 more.
10.
Alright. So is that one, that's one that we can actually get a general term for, because 1, 3, 6, and 10 will follow this pattern, n times n, is it plus 1 over 2? Does that work? So Gianni, when I put in a 1, do I get a 1?
Yes.
What about when I put in a 2?
Yes.
And a 3?
Yes.
Alright, I think that's it. So, what do we do with that? Do you remember, Morgan? We wouldn't have to do any of this who struck if we could always come up with this term that represented the partial sums. So what would we do with that, Morgan, to find out if it converged or not?
You set it equal to limit as n.
You take the limit. So on this one, what happens to it when I make n go to infinity? What happens to that expression?
Infinity over 2.
Yeah, so that's just infinity.
Infinity.
Right, so you divide infinity in half, you still have infinity. So therefore, this is a diverging series. So it'd be nice if we could do that with everything, but the weak part is right here, where we often figure out what that is. So I keep showing you ones that we can. I don't know if that's very convincing, but most of them we can't come up with this. We see this nice advancing partial sum sequence, but we can't come up with the general term. So that's why this only works in a limited number of cases. So then we went to the telescoping ones, and do you recall these, Jonathan? How would you set this up for telescoping? I'm not going to do it, we're just going to discuss it. It doesn't look very telescoping at this point. Telescoping usually has one term minus, with often a numerator and a denominator, minus another one. So what little algebraic trick do we have to pull out to make it telescope? Do you recall? It was like one of our 9.2 camps, when we camped in 9.2 all those days.
Not Loki Tell.
Nope.
Because, yeah.
We were going to try to make this look like this. So I think this one actually comes out to be a 1.
Oh yeah, 2. You take out these 2 fourths, I think. Oh no, wait.
I don't know which one I want it to be plus, doesn't matter. This is, I'm not sure this is actually equal, it might be, but how would I have got, that looks telescoping, because the first term would be like 1/3, and then it would cross out, first it's 1, then minus 1/3 plus 1/3, minus 1/5 plus 1/5, and so on, something like that. So with that in mind, everything drops out except the first term and the last term. But how did we get from here, algebraically, to here? You did it back once upon a time in 9.2. You have to recall that comes out. Brendan, can you help us? What was it?
Is it something that we've done in the past?
Yeah.
Is it partial fraction?
Partial fractions, right. Remember, we factor this and we do A over this and B over that and so forth. And I think this probably the n plus 1 was over here. I don't know. One of them, this is I'm just trying to do from memory, and I don't have much of a memory. So, but it's going to look similar to that. And in the end of the story, it's going to create a 1 in the front, and at the end, it's going to have this term. So what did we do with that? Do you remember, Gianni? We would say the first term was 1, everything else would bleep out, and then we'd have this last term lingering around. And what would we do with that?
Plug in infinity.
Right, we would take the limit to see where this is going, because n means we're stopping somewhere. And n equals a million billion, but still you're stopping. We're not stopping, this is infinite. So then this, and every single one of them that went to 0, but you had to check. And so then you ended up with those terms that did not cancel each other out. Sometimes there was more than just the first term, so you did have to write them out to see. So remember that telescoping series? Then we went on to geometric, which has telescoping kind of dropped out of our scopes because it just hasn't seemed to appear in our problem sets. But the geometric did appear and it stayed with us. So the geometric one looks like this. It has some first term and then some r raised to the n, and it went from 0 to infinity. So Morgan, what was the hoopla about that when we had to check a certain form of these geometrics converged and certain ones didn't? Do you remember what the parameter was?
R is greater than 1.
Right, so actually the absolute value is greater than 1. So it could be like a negative 1/3 would also, and so what were these?
Diverge.
Diverge, right. And then when it's the other way, it converged. And we could even say to what it converged with the formula. But we're kind of staying with that question today. All right, so you saw those in even last night's homework, and they're going to keep on, so be ready to recognize them. Then we went on to the nth term test. So the nth term test was like that. So the nth term, this is the nth term. So Jonathan, what did the nth term tell us to do? The nth term test, what were we testing for, and what do we do with it? Do you recall how that worked? That's the ones that I was helping you with today, I think.
You take limit to infinity,
right.
From n to infinity.
Right. So the test says if this term does what in infinity? Do you recall? What are we looking for?
Whether it converges or diverges.
Right. And if this term, just this term, if we take it to infinity, then if it, like you're saying converge or diverge, but what were we actually looking for?
Oh, whether it's less than 1.
That wasn't that one. That was geometric.
Whether if it's 0? Wait, what?
The nth term test.
The nth term.
That's why I thought. That's why I kind of start over every day, because every test is different and it gets all jumbled up. Brendan, what happens in the nth term test? What are we looking for?
If it diverges.
Yeah, that's right. So it's the nth term test for divergence. And how did you know it diverged?
If it wasn't a 0.
Right. So the only thing we care about is whether it's 0 or not. So what happens to this one, Brendan? This particular one?
It would go to infinity.
All right. So is infinity? Is that divergent then by the test? What if it had said 1? Would that be divergent? Mm-hmm. Yeah. So it's anything but what?
0.
Or 0. And what's 0 tell you on this test?
No conclusion.
Right. All right. So when it's 0, that tells you the terms are getting smaller and smaller and smaller and smaller. So we're looking for terms that are not doing that in this test. All right. And then yesterday we noticed that for certain ones, when the police and the cops and the detectives came out and saw that for at least x greater than 1, it's positive, continuous, and decreasing. So if it meets all those requirements, then we could use this test. So Gianni, what do we do with the integral test?
You check to see if it met all the standards.
And then,
And
so
then
say like 1 over n, it does. So then what?
And then you take the integral of it. And
Right.
if the integral converges.
And what kind of special integral always pops up?
Improper one.
It's improper because we have infinity in one of our limits. And so this one actually, once we took the ln, because ln was involved, it actually diverged. Do you remember the name we gave this special one, Morgan? Pythagoras thought of it first.
Not really.
This one was
Harmonic.
right, good, harmonic. So let's and part of our discussion with the integral test was something called the p-series, and that was when they looked like this. And so that was sort of a special case for the integral test. Jonathan, do you recall p-series? Like she just told us that this one diverged. What about, do you remember how to apply the p-series, the principle that dictates those that look like this? We call them p-series. Do you remember which ones diverge for what values of p and which ones converge? Obviously this one, p is 1, so it diverged. So that might be a hint.
This is yesterday. What was this?
Yeah, it was yesterday.
Was
Okay.
it? Well, we didn't meet yesterday.
Wednesday.
Or what? Okay.
So you weren't
this
here?
was from the video then.
Okay. It was the very last thing I crammed into the board, like right here. I'm a visual learner, so I have to...
If p is less than
Got it.
or equal to 1,
Right.
then it diverges.
Alright, so then Jonathan, what would p be in this one? 1 over square root of n. What would p be?
It's 1. So it diverges.
It is divergent, but p isn't 1.
Or wait.
What is it when it's square rooted? What value? So I'm going to write this in this form. What would I write here for p to represent this problem? P to n to the what? Not 1. That's not equal to that. That's equal to that. But what would we put here? What p would it be? What number represents square root?
So 1/2.
Right. So is that divergent according to your rule? 1/2.
Yes, because it's less than 1.
Right. Exactly. All right. So
Miss Val.
now let's. All right. Let me just finish these.
Okay. It's
All
been
right.
13 minutes.
Oh, okay. You better cut it off then. All right.
Oh, I
Part
get it.
2.
Oh, okay.